All right, we're on to lecture B. We just talked about in lecture A. Just finished talking about parametric curve example with straight line motion. Uniform means at a constant speed. Okay? We did a graph, a static graph, like that. Ideally, you want to do it dynamically. Now, your calculator will automatically do that. When you do the parametric mode in your calculator, it'll automatically show you the graph being traced out at the appropriate speed, you might say, at least as far as the calculator lets time increase. In Mathematica, we can do it as well with manipulate. I'm not going to take the time to do that. I don't think I have enough time for that, but for sure we'll look at that on next Monday. You can ask questions like, how far did the bug travel? And what was the bug's constant speed? And something else we can do with Mathematica next Monday, we can play with the equations, try to produce other kinds of motions along the same line, but maybe not at a constant speed, for example. Or maybe in the opposite direction. I'll show you that on Monday. But what's the distance traveled? Well, it's the length of that line segment there. You can use the Pythagorean theorem, right? Draw a right triangle in here. Or just use the distance formula. Looks like this. What did I do there? I am taking the square root of a sum of squares. Coordinates these points. This one's 4, -8. This one's 1, -4. -1 minus 4 is the difference of the x coordinates. I'm squaring that. I could have also done 4 minus -1. Either way, it squares 25. And then 4 minus -8, this coordinate minus that coordinate. I could have also done -8 minus 4. When you square it, either way, the answer is 144. 25 plus 144 is 169, and I purposely picked this to be a nice square root. 13 centimeters is the distance traveled. What's the constant speed? Well, I'm saying it is a constant speed. I actually haven't proved that, but it makes some sense because these are, again, linear equations in t over here, if you want to look on the left again. Those are linear functions of t. Those have constant rates of change. It should make intuitive sense that the speed of this motion would be constant. It is. I'm telling you it is. And what is that speed? Just do distance divided by time. Great. Equals distance divided by time. 13 centimeters divided by 10 seconds is 1.3 centimeters per second. That's how fast this bug is moving. Right? Distance equals rate times time, therefore rate is distance divided by time. And I'm assuming it's a constant rate here. Constant speed. Notice in terms of graphs, just like we did the first lecture, way back in September, I realized after I made the PowerPoint that I didn't draw this in the most ideal way, but bear with me here. Think about this, okay? So I've got axes. T, time, is horizontal. The vertical represents two different things. Now, usually that's not something that you want to do. You usually don't want to have two different quantities on the vertical axis. You want to have two separate graphs typically. But we'll do it anyway. So the red graph is, well, the blue graph is the distance graph. Its units would be centimeters. The red graph is the speed graph. Its units would be centimeters per second. The red graph is horizontal. The speed is constant, 1.3 centimeters per second. The speed is the derivative of the distance. You already know that, right? Speed is the derivative of the distance, just like velocity is the derivative of the position. The distance is rate times time. Distance equals 1.3 times t. That's rate times time. Speed times time. That's also an antiderivative of 1.3 as a constant function, right? Integrate 1.3, you get 1.3t plus c. But we're going to take the c to be 0 because we want the distance graph to go through the origin. What else can you say? You can say the slope of the distance graph is 1.3 because that's its derivative, its constant derivative. You could also say the area under the speed graph is 1.3t, which is the same as the distance. Now I shaded this a light blue. It's kind of hard to see if you're in the back perhaps, but there's a light blue shading to this rectangle here. That's an area. It's base times height. The base is t, the height is 1.3. The area of this rectangle is 1.3 t. I picked t to be about 2.6. I could have picked something else for t here. I'm using the letter t for a couple different meanings. Here is just a label for the axis, a variable. Here I'm thinking of it as being a particular number. A better way to have made this picture that I didn't think of until after this was all made, it was like 10 minutes before class, I'm like, well, I can't change it now. I probably should have made these arrows, instead of showing, going to this blue graph, I probably should have made them go to the blue graph down here instead of up here. Down right there, actually, right above where t is. Because at this particular value of t, say 2.6, the speed is 1.3, and the area under this red graph, which is the same as the value of the blue graph, is 1.3 times 2.6. What would that be? 1.69 times 2, 3.38. 3.38. Yeah, seems reasonable. 3.38 centimeters traveled after 2 seconds. But again, I could have picked anything for t. Just pick t. And the principle still holds. And the area of the rectangle still would be base times height, t times 1.3. It still would give you the distance traveled at that value of t. But as t increases, the distance increases. It's an increasing function of t. And it's a straight line. Its slope is constant. That's constant speed. How about circular motion? Modeling circular motion. At a circular uniform motion, so that is at a constant speed. For example, what if a bug walks at a constant speed over the course of 10 seconds around a circle, radius 2 centimeters, starting at the point 20, and traveling, say, counterclockwise? How would you model that motion? Well, let me just tell you the answer. And after I write down the answer, I hope it makes sense. Let x equal 2 cos t and y equal 2 sine t. That'll be a motion along a circle centered at the origin, of radius 2, starting at the point 20 when t equals 0, going around counterclockwise, and ending at the point, oops, this is not quite right, sorry. I want it to end at the point 20 when t is 10. That doesn't need, I need to modify these things. I'm running too far ahead of myself. Not just t's. I want to be back where I started when t is 10. In other words, I want the period of the motion to be 10. And remember, the b that goes in front of the t is 2 pi over the period. Period's capital T. 2 pi over 10 in this case, which simplifies to pi over 5. Pi over 5t in both spots. If I had just t's, then the time elapsed would be 2 pi to get back where we're starting. About 6.28 seconds. Double check, if you plug in t equals 10, pi over 5 times 10 is 2 pi. You're going to be back where you started. Why do these work? It's based on the definition of the cosine and sine functions, the unit circle definition. Right, we did it for unit circle, radius 1. To deal with it for radius 2 circle, just multiply by 2. We found parametric equations for the path. I just essentially told you the answer. The path itself is called the parametric curve. It doesn't necessarily look like it's going to be a constant speed here, because these are not linear functions. But it will be. If you use these functions in this way, it'll be a constant speed going around. You're just trusting me on that. We will eventually prove that. There were infinitely many possible right answers, but once again, we chose the most natural, starting at t equals 0 and ending at time t equals 10. What's the xy equation of this path? Can we eliminate t? And the easiest way to do it in this context is to avoid trying to solve one equation for t and plugging it into the others. Instead, just realize, hey, wait a minute. What's the equation of the circle? I know what the path is already. It's a circle of radius 2 centimeters at the origin. X squared plus y squared plus the radius squared. That's the equation of that circle. If I'm going to be on the circle, no matter what t is, when I replace x with this and y with this, I better get 4. And the key thing that makes that work is the Pythagorean identity. 2 times cosine pi over 5t, quantity squared, plus 2 times sine pi over 5t, quantity squared, is 4 cos squared pi over 5t plus 4 sine squared pi over 5t, and then I can factor out the 4 and get 4 times in parentheses cos squared pi over 5t plus sine squared pi over 5t. And it does not matter that it's some crazy number pi over 5t. As long as these match, this expression will equal 1, no matter what t is. This is a big 1. So this simplifies to 4 times 1, 4, which is 2 squared. We are on the circle centered at the origin of radius 2. How do you know you go counterclockwise here? Again, that's essentially based on the definition of cosine and sine. Thinking about that bug walking around the circle like we are doing now, back in chapter 1. Remember that? About the bug definition of cosine and sine. First coordinate, second coordinate for cosine and sine. The circle is radius 1. And you got to use radian measures when you think about this for t, because then on the unit circle, the radian measure of the angle is the same as the distance along the arc length. I can graph this, it would graph at a constant motion. Again, try this on your calculator, parametric mode. Good to try that today. It'd be ideal to do it dynamically so we see the constant speed. We can ask the same questions. How far did the bug travel? What's the bug's constant speed? And we can do things on Mathematica, which we'll do next Monday. So, how far did the bug travel? What do you think I should use? It's a circle. What's the distance around called? Circumference. You don't need the distance formula. Use the fact that you know the circumference. The radius is 2. The circumference is 2 pi times the radius. Pi times the diameter. 4 pi centimeters, which is about 12.566 centimeters. Just happened to be close to 13, the distance traveled in the straight line example. I didn't plan that, it just happened in the case. How about the constant speed? Distance divided by time. 4 pi centimeters divided by 10 seconds is 0.4 pi centimeters per second, which is about 1.2566 centimeters per second. We can graph, once again, the distance traveled and speed as functions of time. And the graphs are going to look very similar to what they looked before because this is a constant speed. It doesn't matter that the path is a circle. These graphs look pretty much the same. They're not exactly the same, but they're very similar. Instead of a constant speed of 1.3, it's a constant speed of 0.4 pi, which is close to 1.3. This red line is a little lower than the one in the other slide. Instead of constant slope of 1.3 like we had in the other slide, this constant slope is 0.4 pi, 1.2566. Notice it does not make it up to 13 like the last one did. If it was 10, it makes it a little lower, 12.566. Once again, the slope of the blue graph, the derivative of the blue graph is the red graph. The speed is the derivative of the distance traveled. The distance traveled, 0.4 pi times t. This area of this lightly shaded thing here, maybe zoom in if it's hard to see the color there. There's a light blue color there for this rectangle, for this fixed value of t. Base times height is t times the height of this, which is 0.4 pi. that area is 0.4 pi times t, which is the same as this distance traveled. And again, it would have been better for me to put these arrows pointing toward that point right there above this value t at about 2.6. Same themes as before. Again, it doesn't matter that the motion's along a circle when I make these graphs. How about non-uniform motion in the plane? Non-constant speed. Remember on lecture 1? First we did the cars traveling at constant speeds, though they were different speeds. Then they were doing herky-jerky kinds of things, right? Remember that? And I think we did the same thing with the flow of the colored water into those vats. And with the populations, I think that might have been harder to see. What about a non-constant speed? Well, there are lots of possible answers because there are lots of possible non-constant speeds. Going back to the straight line here, by the way, if you didn't notice that. Starting at 4, -8, ending at -1, 4. Straight line. This is still going to be straight line motion, but not with a constant speed. What I can do is I can take my answers from the first straight line we did. Oh, do I remember them offhand? I think f of t was what, -1/2 t plus 4? Is that right? And y equals g of t. Oh, I forgot that one. Can I refigure it out? 615 minus 8. What I can do is I can take those same equations and replace t with something else, like maybe t squared. So that doesn't quite match the ending point when t is 10. If I replace it by t squared over 10, though, it does work. T squared over 10 is 0 when t is 0, and it's 10 when t is 10. Bring it there and there. I get two nonlinear equations for x and y involving t squared. The motion is still along the straight line. I could still eliminate the t by eliminating t squared, just like I did before, and get the equation that I had here but I erased for the line involving no t's. Be the same process, except I'd be doing it with the t squared instead of the t. But because it's a t squared, the motion is not a constant speed. It's going to get faster and faster. The bug starts running faster and faster with this little bug. Like a cockroach or something. It's running faster and faster. It accelerates. We can graph this. We can figure out how far the bug travels and what's the bug, not constant speed, but instantaneous speed at any moment in time. Maybe. Sounds like a derivative, right? Here's what the graphs look like in this situation. The speed is not constant. It is a linear function of t. It's this particular linear function. How do I know that? I'm not going to say right off the bat. It is increasing. There's a constant acceleration for this bug. Which makes some sense. I mean, if you think about up-down motion with the t squared involved, the acceleration is constant. Force due to acceleration due to gravity. The derivative of the speed is constant, 0.26 would be the acceleration. I'm not explaining how I got that here. The distance turns out to be a quadratic function, 0.13 t squared. And by the way, when t is 10, this does equal 13. That's 0.13 times 100. 13. That's the distance traveled. It's no longer straight. It's a quadratic. It's a parabola. But the same principles still hold. Its slope at any time, t, its derivative is 0.26 t, which is the speed. Conversely, if you shade an area, zoom in here, onto the speed graph, that's a triangle this time, up to some moment in time t, I may be 4.7, I think, this time, instead of 2.6. the area under that speed graph, 1/2 base times height, is the same as the distance traveled. Why? The base is t. What's the height? The height is 0.26 t. 1/2 t times 0.26 t is 0.13 t squared, the distance traveled. And that's an antiderivative of 0.26 t. You differentiate the distance to get the speed, you integrate the speed with the distance. Though I do want, since I'm starting at time 0, I want the blue graph to go through the origin, so I don't put a plus c. I just do 1.13 t squared, because when t is 0, then the distance traveled will be 0. Generalizing our observations. Hang with me here. These last 10 minutes are super important. Generalizing. In each example so far, the speed is the derivative of the distance traveled. It's the slope of the distance curve at time t, for any t. In the last example, the distance curve was parabola. At any moment in time, I can figure out the slope of the tangent by taking its derivative. And that gives you the speed function, which was a straight line. The slope of the distance traveled function is increasing. It's a concave up graph. And think visually on these things when you hear these words. You gotta pay attention to what I'm doing with my hands. What else? And because the motion starts at time 0, the distance is the integral of the speed. But don't do a plus c, where c can be anything. Choose the c so that this function, this formula, whatever you get, goes to the origin, its graph. Goes to the origin. Speed of 0, distance of 0 better be 0. These are functions of t, by the way, speed of t and distance of t. And we've seen also that it's the area under the speed graph. Like in the last slide, it was an area of a triangle. Gave you the distance traveled. This calculation right there. Okay. These facts generalize to any such situation, no matter what. The bug could be flying through the air in three-dimensional space, speeding up and slowing down, stopping to look at a picture of the Mona Lisa, going around in corkscrews. Its distance traveled function will have a derivative that it's its speed. That's not surprising. And conversely, its speed function will have an integral that's its distance traveled. I guess that's not so surprising. What's most surprising is the antiderivative, the integral, is an area under the speed function. No matter how crazy the graph that speed function looks. No matter how crazy the motion is. The distance traveled is the area under the graph of the speed function. That is essentially the fundamental theorem of calculus, right? And it's amazing how many applications it has. Not just the motion. More commonly, notationally wise, this last equation here is often written as what's called a definite integral instead of an indefinite integral. And here's the notation for it. Distance of t is an integral, put a 0 down there and a t up there, of the speed. I have purposely put a different letter here, u, but then I'm also saying this is the area under the speed curve from time 0 to time t. What is u? U is called a dummy variable. Why? Because it doesn't matter what letter you use. Anything other than t or d would be okay here. We don't want to use t or d because we've already got places for t and d. Although I will tell you, some scientists and engineers, they go ahead and put a t there and there anyway. It's not really a good idea. And I don't want you to do it. Put some other letter there. U is a common letter to use. Just another letter to make. What's going on here? If the speed graph The speed doesn't even have to start off with the speed of 0. You can start off with a non-zero speed. If the speed graph looks like this, this is the speed graph. I'm not going to write speed of t, I'm just going to write speed graph. And we start at time 0. You can say maybe u equals 0 here. In a sense, u represents time, just as t does, but I'm trying to think of t as something specific here. And here's u equals t. U is kind of the variable here. T is something specific. What this is saying is the distance traveled from time 0 to time t is this area. That area equals dist. And here I will put a t, distance of t. Though I can change t then, right? Whether something's a constant or a variable is all in your head. It's all in how you're thinking about it. And thinking about it in different ways is helpful. In fact, as t increases here, the area gets bigger and bigger. So the distance graph, if I graphed it, does have to keep going up. It's got to be an increasing function. Because you're moving, right? What is the motion here? Starts off kind of fast but slows down. Then it goes faster and faster up here. Then it slows down a little bit. Then it goes faster and faster up here. And here it's kind of leveling off in its speed. Not its distance traveled. It's leveling off in its speed. The definite integral essentially is defined to give an area on the speed curve. Now the definition of this definite integral technically involves limits in a way that I'm not going to say today. The definition of this area. It does go back to lecture 1 and in fact Stephen Strogatz's lecture about calculus breaking things apart and putting them back together again. Letting the number of pieces go to infinity, essentially, it is related to that. But I'm going to ignore that for the moment. We'll talk about that the week after Thanksgiving. Not even on Monday. Essentially, it's defined to give you the area. Here's our last slide for the day. The Fundamental Theorem of Calculus. Sounds important, huh? Yeah. Isn't it more important than mean value theorem? Probably, but mean value theorem has initials M and BT, and so it's fun to pretend it's the most valuable theorem. It's essentially the discovery of this theorem by Newton and Leibniz that is the birth of calculus. Before Newton and Leibniz, people figured out areas of things. They figured out slopes of tangents. For special cases, at least. Newton and Leibniz unified those ideas and also generalized them to solve more problems. Yes, its essence is to relate slopes of tangent lines to curves to areas under other curves. Slopes of tangent lines of some function gives you its derivative. When you find areas under the derivative, you get back the original function. Like distance and speed. Here's a more precise verbal description in 2 ways. The quote-unquote area under the curve function is an antiderivative of the given function. Or that means the derivative of the area under the curve function is the given function, the curve itself. Kind of confusing. This is the given curve, the speed. The area under the curve function, this function, is an antiderivative of the speed. If you differentiate this, you'll get the speed. Said another way, well, I guess I did say it both ways then. And again, it's this connection to area that is the new main thing here. This connection to area of the graph being important. The important connection between derivatives and antiderivatives. Here is the formal statement as a theorem. Suppose f is a continuous function on a closed interval, little f. Define a new function, capital F, by this formula. Integrate little f from A to x. In other words, if the graph of little f is above the axis and A is right here, say, capital F of little x is this area. This area equals capital F of x. The integral itself is just, this definite integral is just shorthand notation for that area. We could call it area of x, but there are good reasons to use an integral sign. Or we could call it distance of x, or distance of t. Then capital F is differentiable, and its derivative is little f. Capital F is an antiderivative of little f. Symbolically, we can write it this way. The derivative of this integral is the function you're integrating. If you think about it, that is true. What this statement is, actually, is found in your book in chapter 6, which I have not assigned in the reading yet. I am going to assign it over the weekend. There are two forms of the Fundamental Theorem of Calculus. This form you will find in section 6.4, which is past chapter 5, of course, which we haven't done yet. This is the harder one to understand. There's another form that's a little easier to understand. A little bit, at least. Or maybe you might say is more commonly used. Taking calculus before, you might recall doing capital F of B minus capital F of A. That's what we're talking about for the other form. I'm going to have you read ahead a little bit in spots in chapter 6 before we do chapter 5. Chapter 5 we're not really going to come back to until the week after Thanksgiving. Okay? But what I've told you today is the essence of the most important stuff for the rest of the course. But then we'll also look at applications. All right, have a good weekend.